Hello everyone, this is Wei Yuan. I'm the co-author of Circle Continual Repair Across Programming Languages. So I'm here to introduce our work published in ISTA 2022. So before introduce our work, I would like first to introduce the basic idea of automatic program repair. So what's APR? APR aims at fixing source code with less manual debugging efforts, which plays a vital role in improving software reliability and development productivity. So generally, the input of APR model is buggy code and context code, which is optional, and the output is fixed code. So as you can see in the figure, if in the DL-based APR, our model is generally based on NMT models. So these are some typical existing works. The first work is Coconut, which separately encodes code context and buggy codes by CNN networks. So its structure is in the left. And sequence R abstracts the buggy context and takes it as input together with buggy lines. So its structure is in the middle side. And Q is an advanced coconut. It employs GPT as token embedding layers and and the rest side is the same as coconut. So its network structure is in the right side. So recently pre-trained model is very popular. So someone use BERT to fix Java simple bugs, and its network is here. So if you are interested in this work, you can just read their paper, and I list the paper here. However, for this existing work, there are some limitations. For example, for the first limitation is that most of them can only fix bugs for a single language. So that means if we want to repair codes for many languages, we have to train and store a corresponding number of models. And in addition, these models are trained independently. So that means we cannot transfer the latent knowledge learned from other languages. Another limitation is that they are developed in an offline manner. So that means they cannot continually improve their bug fixing ability. So for example, when we want the model, after we will train a model and we want the model learn new task or learn from new data, we have to retrain the model on the whole task and data, which is very inconvenient. So to mitigate these issues, we decide to propose a new deep learning-based APR model, which can process multi-type programming language and continually learn how to fix bugs. However, to propose such a model, we have to address two challenges. The first challenge is that obviously repairing bugs across languages is more difficult than for a single language. So to achieve that, we have to learn how to effectively and efficiently exploit the power of deep learning, especially the large pre-trained neural network models, which are popular in NLP. Another challenge is that when model try to continually learn tasks, they are prone to forget the knowledge obtained from previous tasks. So how to prevent catastrophic forgetting is not trivial. So to address these challenges, we first propose a prompt template with a T5-based APR model and a repairing mechanism to solve the first challenge. And for the second challenge, we propose a rehearsal method and an elastic regularization method to achieve continual learning. So here is the overview of our circle. And the figure illustrates the structure of our circle. Generally, circle has 5 components. The first one is prompt-based data representation, and the second one is T5-based API model, and the third one is difficulty-based example replay, and the fourth one is sampling-based EWC regularization, and the last one is cross-language repairing mechanism. So let's first introduce prompt-based data representation. So we utilize, generally, the basic idea is that we want to transfer API task into a fill in the blank task so that T5 can, it's more natural for T5 to fine tune on such data set because the T5 was pre-trained on fill in the blank task, right? So here we use some special prefix like buggy line, context, and the fixed code is. We use this prefix to concatenate the source code and context code and prompt our circle to generate the correct code. Also, we use T5 as the skeleton of API model. T5 is a very commonly used large-scale pre-trained language model. It contains an encoder and a decoder. The encoder is a pile of scattered transformer blocks. It contains a multi-head self-attention and a position-wise feedforward network. And the structure of decoder is much similar to encoder. However, it contains causal attention to avoid information leaking. To avoid the catastrophic forgetting, we use an example replay method. So the basic idea of example replay is that we want to retain a small set of examples from the past training data and replay these examples in later training tasks. So the key idea is how to choose examples. Here we decided to choose difficult examples. So how to define the difficulty? Here we simply use loss value normalized by code length as the difficulty because we find that the longer the loss is, the longer the length is, the larger the loss value. So we do not want the length be the only factors. So we just normalize length as our difficulty. However, if you just use, example replay, it's not enough because the size of example sets should be as smaller as possible. So here we apply a sampling-based EWC regularization method to mitigate catastrophic forgetting further. So what's EWC? The basic idea of EWC is to put more restriction on important parameters so that it can forces the model update less important parameters more, so that we can alleviate forgetting for the past tasks. However, directly calculate EWC is very time consuming, so we just calculate on the selected example set and we use M as the threshold so that we can further reduce the calculation time. The last component is repairing. Since T5 is a natural language generation model, so the generated content, its format is not as restricted as programming language. So it suffers some format issues. The first issue is that the keywords mismatch. So that means generating keywords that have the same semantic meaning but belongs to other languages, like noun in Python, null in C, and the lower letter null in Java. So noun null are their semantic meanings are much similar. So sometimes T5 will misgenerate them. Another issue is format mismatch. So that means we generate correct tokens, but with some with incorrect format. Like we generate two equation sign, however, we generate an extra space, so which is incorrect in Python. And the third one is slightly suffers OOV problems. So for some very real tokens in NLP, but these tokens are very popular in programming languages, T5 will suffer OOV. And we test many symbols, and only 3 symbols, luckily only 3 symbols suffer this problem. So we, so for these 3 issues, they are very simple format problems. We just need to build some templates to transfer the T5 generated contents to new contents, and these contents will have very high quality. Here is the setup of our experiments. We have 3 research questions, and we conduct our experiments with 4 popular languages: Java, Python, C, JavaScript. And we assume each task come according to the popularity order. And the dataset is identical to Coconut. And we use Defect4J, quick bugs, many bugs, and bug IDs as our benchmark. For RQ1, we use fine-tuned APR as the baseline, and for RQ2, we compared with more than 30 APR models. So for RQ1, as you can see in the right figure, compared to the conventional fine-tuning method, our circle can continually learn bug fixing. For RQ2, we compared with 30 state-of-the-art APR models. And as you can see, for all the languages and all the benchmarks, our model can achieve comparable and even outperforms than these SOTA models. And it is worth to mentioning that these SOTA models can only perform on a single language. So that means for different languages, we have to train different SOTA models. However, for our circle, we use one model to compare with all these models. Also, we investigate the components contribution, and as you can see, prompt can let our model achieve more optimal performance, and repairing can repair this, these 3 format problems we mentioned before. And the continual learning model can let our model achieve continual learning. We also conduct a case study to answer the question, can the model distinguish different meanings of the same keywords among different languages? So for example, def is a keyword in Python, but it can be a variable name in other languages. So will this let our model be confused? We investigate this problem. So we choose Java and Python version of Bitcom, and we replace the variable name n with def in Java and replace n with public in Python version. So as you can see in the right side, our model will not be confused with such setting. So here is the contribution of our work. We propose Circle, which is the first APR model that can fix bugs across languages and achieve continual learning. Also, our model contains 5 components, and we conduct extensive experiments on 5 bug benchmarks with 4 commonly used programming languages to demonstrate the effectiveness of our proposed methods. And since this is a very brief introduction of our work, if you are interested in our work, you can just feel free to read our paper. And yeah, that's all. Thanks for your listening.